Hey, I'm Nathan.
Hi, I'm Julia.
And I'm Megan. Our project is building a routing protocol to run on a virtual network. In our own research, we noticed that there weren't a lot of comprehensive open source materials that walk students through this process, and not everyone has the privilege of taking a computer networking course. So, another part of our project is to provide full documentation of how we completed our project so that other students can dive a little deeper into routing and computer networking using the information we've already gathered and be able to create their own protocols. The main components of this project are a virtual network utilizing Docker and VRNetLab to virtualize the routers, a link state interior gateway routing protocol implemented in C and C++. This means that the protocol will run on every router within an isolated network. Um, and as the name Scenic Routing suggests, the protocol will aim to route the packets the longest possible path to their destination or taking the scenic route. And the last component is the network visualizer that will monitor the flow of information on the network in real time, and it will be implemented using Unity and Elk Stack.
Hey, everybody. So, for this project, the way we connected our parts was for the routing protocol. We needed to find a way that we can make a virtual network that would be suitable to be able to scale up or down, just depending on how we're trying to test our protocol. So, I found Docker, which was essentially not the first idea I had. The first idea was a virtual box, but that just turned out not to be a good way to create a virtual network. Um, and so using Docker, it allows me to create containers that will contain open-work routers. And these containers are essentially just a packaged bundle that holds all the necessary. Hey guys, so for the network topology, I began using Docker containers. Doing this was allowing me to contain each of the openworks in their own space, and then also for the virtual connections between the routers, I used XCon, as you can see, which is right here. XCon's a part of a software I'm using, which is Vernet Lab, and a Vernet Lab allows me to use open software routers inside containers. So this worked out well for us as we are already using OpenWork. Here, as like I was saying, XCons themselves, that is a virtual, or that is a container, and then so are OpenWork 2 and OpenWork 1, and they're pinging each other back and forth using the container that encloses the virtual connection between them. And that's done using the WAN interface.
An important part of our project so far was designing the routing algorithm we would use to take packets, the scenic route. However, a network is an undirected cyclic graph, so modifying Dijkstra's algorithm to take the longest path instead of the shortest path wouldn't work. So instead, we're going to create a maximum spanning tree using Kruskal's algorithm by negating the edge weights, and then using breadth first search to find the path between the two vertices. A spanning tree is a connected subgraph that covers all of the graph nodes with the minimum number of edges. So a maximum spanning tree is the spanning tree with the largest possible edge weights. An example of a maximum spanning tree is pictured to the right. Breadth first search is an algorithm used to traverse a graph by exploring each level of depth starting at a root node. The algorithm I mentioned previously is certainly longer than the shortest path, but not quite long enough. So I've added another piece to the algorithm. If the destination node is only one hop away from the source node, append the longest loop to the path that does not include the destination node. For example, if we look to the graph on the right and A to B is our original path, we would then add the loop ACDA to the new path, giving us the final path ACDAB. This means that before making the maximum spanning tree, I will need to use the graph coloring algorithm to keep track of all the loops in the network to be accessed later and appended to these two node paths.
So coming into this, I never had any experience with networking or virtual networking. So it took a bit of time to try to get myself caught up to that, just to understand how I would create a virtual network. So that was the first bit of my development stage. The next bit was trying to find a suitable source to create a virtual network. I started with VirtualBox, but found that to create the VirtualBox and to implement it for testing, um, it just wasn't doable. Um, if we had more time, it could be, but I found another program, Docker, which is a highly used software, to be much more feasible to create a virtual network. So here in the picture, you can see that some of the virtual or some of the containers I used are here. So you got two OpenWork containers, OpenWork 1 and 2, as I previously shown, and then VerXCon, which was the one that was communicating the two containers. This one here is just an extra connection, so you don't have to worry about that. So using containers to create a virtual network will allow us to scale our network up or down and allow better testing for the routing protocol. And so that was the major developments for the network. The major developments for the network, um, as I previously stated, I was using VirtualBox. That became to not work out well, as it was just too hard to create the connections between the routers and then trying to make it all communicate without using false networks, such as like they're all connected to a main router. So I moved to Docker, which found to be much easier in the sense that we're able to start to create virtual connections between each other. And this allows me to enclose the network to create a more realistic style, more compared to like a physical network.
So here are the major developments I accomplished this semester while working on the routing protocol. The first thing I did was I set up an OpenWRT build system to create packages to run on a router. My router in this case is a VirtualBox machine. Um, OpenWRT is a Linux distribution that allows me to upload packages to a wireless router without having to flash a complete firmware image. So this makes it easier to just build an application and have it run on the router without having to do anything extra as I implement changes. So the picture to the right is an example of me uploading a package using the build system, installing it, and then running it on the router. Another big accomplishment was designing the longest path algorithm, which was actually really hard because I had to think about what it meant to find the longest path, and how I wanted to go about that while limiting infinite loops. Lastly, like my every step that I did, with like the build system, designing the longest path algorithm, all the research I did, I had to document all of it so that someone else could look at it in the future and either recreate what I did or use the knowledge for the foundation of their own projects. I ended up having about 25 pages worth of documentation. So with the build system all set up and the routing algorithm design, the next step is to implement the routing protocol in C and C++, and then run that on the routers in the virtual network that Nathan is creating.
Much of the work done this semester with the network visualization tool was research and documentation. There are not a lot of resources out there for network visualization tools. Some of the tools that do exist aren't open source, and the vast majority of network visualization tools or network graph tools are for static rendering of network data rather than our goal of trying to render the data dynamically and do that in real time. So in doing research, a lot of the processes were looking at languages and tools that allowed for rendering graphics to show network data and narrowing those down based on what would work with our goals, eventually settling on Unity and C#. Now, I was able to find a sample project, a student project done in 2017 called Ergo Witness that does actually render network data in real time and queries the network using logstash and packetbeat to filter results from the elk stack. The really nice thing about this project is it is open source and fairly well documented, so it gave me the opportunity to begin looking into these technologies. There is still a lot to learn, so I've begun researching the configurations needed in the machine setup in order to work with this project. So in addition to cloning the project down from the Ergo Witness GitHub, I have also been working on setting up the virtual machines. So I have a VM that runs CentOS, which is a bit of a process to install, and I still need to configure with ElkStack. So there's a machine running for the network queries, and then there's a machine running the Unity visualization tool. So on the upper right, you can see the CentOS, and on the bottom right, that is a screenshot from the visualization tool Ergo Witness. So what is next? The first thing I really need to do is finish the configuration of both machines and get that set up to work with the Elk stack. From there, I need to connect to Nathan's network so that I'm viewing our data and to confirm that the queries are returning the data that they're supposed to. And finally, building out the interface and all the assets in Unity and figuring out the classes and the scripts needed to manage objects within the Unity project. And that wraps up what I've done and what I have in progress for the visualization tool. Thank you for listening to our presentation. Are there any questions?